Today we're going to be talking about exponential models. Previously we have been looking at linear and quadratic, and now we're going to be comparing those to the exponential. If we think back to previous units, we have talked about exponential functions, so we should have a main idea about what those equations and graphs look like, but we're going to be going through some review now. So you have the option of accepting one of two jobs. Job A offers $20 per hour wage with a $150 increase per year. Job B offers $20 per hour wage with a 7% increase per year. If you are staying with a job for at least the next 5 years, which would you take? So we want to look at these jobs separately and compare. So job A, we can create a table of values for each. So we're going to have our number of years, and our wage is going to go here. So at year 0, we're starting at the $20 per hour. Job A, you're increasing by $150 each year. So at year 1, it's going to be $21.50. At year 2, $23. Year 3, $24.50. Year 4, $26. Year 5, $27.50. Okay, it's saying at least 5 years, so we can calculate up till year 5. If we look at job B, we have our number of years, our wage. So year 0, still starting at that $20. Year 1, we're increasing that by 7%. So 7% as a decimal is 0.01. So we're doing 20 times 0.01. Sorry, 0.07, not 0.1. And we get a $1.40 wage. So that brings us to $21.40. Year 2, we are multiplying $21.40 times 0.07. And we get $1.50 raise on that, so $22.90. At year 3, it'll be the $22.90 times the 7% to give us $24.50. Year 4, $24.50 times the 7%, and it's bringing us to $26.21. Sorry, we're rounding to 22 per hour. And then at year 5, we'll be at 28.06. Okay. So if we compare our two table of values that we've created here, we see that job A starts off better, and then at year 3, you end up making the same amount at both jobs. Past year 3, you're making more at job B. So if we're staying at least 5 years, we are going to want job B because it has the higher wage, reaching that many years. Okay. So looking at each of these, job A is going up by the same amount every time. It's the 150. And that means this one's linear. Job B is going up by 7% each time, meaning it's going up by a new amount each time. So up by a larger amount each time. Okay, so this is exponential. Now, if we're looking at the equations for these, for job A, we're going to have y equals, we're starting at the $20, and we're adding 150 per year. So that's the equation for job A. For job B, we're starting at the $20. We are adding 7% each time, and that's getting multiplied by the number of years. Okay, so here is a linear equation, and here is an exponential. Okay, so looking at our exponential equation, y equals ab to the exponent x, remembering here that the a value is the initial or starting value, and b is the rate of change, so whether you have growth or decay. So our b can look like, if we are going up or down by 1%, our b can actually equal 1 plus r or 1 minus r. Okay, so this is a growth percent or a decay percent. If we're talking about doubling, b would just be 2. If we were talking about half-life, b would be a half, and so on. It's when you have the percents that you can put it into this form here. Okay, so a table, instead of equal differences, exponential models will give a common ratio, meaning when you're dividing the bottom number by the top number, then and continuing down the chart, those numbers will be the same. So when we have linear and quadratic, we have the first and second differences where we're subtracting. We are actually dividing with exponential, and those divided numbers would equal the same amount. Okay. And our graph, so exponential growth, is looking like so, and our exponential decay is a graph that looks like this. Okay, so comparing tables. Identify each as linear, quadratic, or exponential. Okay, so like I said before, our linear is going to be our first difference is the same. Quadratic is the second difference is the same. And our exponential, our common ratio. So when we divide. Okay, so we can always start off with our first and second differences and see if those work. If not, we'll try out a ratio. You can also sometimes tell just by looking at the numbers, and if you see a pattern there, then it's easier to pick between the three there. So the first one, let's find our first differences here. So 12 minus 8 is 4, 18 minus 12 is 6, 26 minus 18 is 8, and 36 minus 26 is 10. Okay, so our first differences are not the same, so we know it's not linear. Let's check our second differences and see if that works. So 6 minus 4 is 2, 8 minus 6 is 2, and 10 minus 8 is 2. Now, because our second differences are the same, this is quadratic. Looking at the next one, checking our first differences, 13 minus 17 is negative 4, 9 minus 13, negative 4, 5 minus 9, negative 4, and 1 minus 5, negative 4. So what we find here is the first differences are the same, so we can say this is linear. Okay, and looking at the last one, if we look at the numbers here, we can see that this is decreasing by a common amount as you go down. Let's try out the common ratio here. So 32 divided by 64 gives us 0.5. 16 divided by 32 gives us 0.5. 8 divided by 16, 0.5, and 4 divided by 8, 0.5. So that gives us a common ratio. When we divide each of the numbers, we get the same amount. So because we are dividing here, we get the same amount. This one is exponential. Okay, so it might take a little bit of trial and error to figure it out. You might have to go through the first and second differences, and if those don't work, then you would go to the common ratio and see if that works. Okay, so that's our table of values. Now looking at our equations. So we already know that if we have a linear, we have just an x to the exponent 1 in that equation. If we have a quadratic, we know that we have an x squared in our equation. And if we have an exponential, we know that we have an x in the exponent. So looking at the first one, y equals 3x squared. We have the squared here, which means we have a quadratic. The second one, we have an x as our exponent, which means we have an exponential function. Y equals negative 2x is the next one. We have an exponent of 1 when there's nothing there, and it's an exponent 1. That means this one's linear. Y equals 4 times 0.5 to the exponent x. That exponent x indicates we have an exponential. Y equals 9 plus 3x. Looking at the x, there is that invisible 1 again, making this one linear. And y equals 9x squared plus 3x minus 8. With this one, we both have an x squared and an x. We look at the highest exponent that we have in the equation. The highest exponent here is 2, making this quadratic. The money in a long-term GIC is shown below. So we are given the number of years and the value of the GIC. We want to determine if this relation is linear, quadratic, or exponential. First, so we're seeing if the first differences would be the same, if the second differences would be the same, or if they have a common ratio. Okay. If we remember back to our exponential functions unit, we know talking about finances and interest falls easily into that category, so it might be a good guess to try our common ratio first. So if we have the 11,000 divided by 10,000, we get 1.1. If we have 12,100 divided by 11,000, we get 1.1. Our 13,310 divided by 12,100, 1.1. 14,641 divided by 13,310, 1.1 again. Continuing on with our last two, our common ratio, 1.1, 1.1. So finding the ratio for all of these, we get 1.1 for all of them, so we do have a common ratio, making this exponential. So find an equation to model this growth. So since it's exponential, we know we need to be in the form y equals ab to the exponent x. Okay. So our a, as a reminder, is our starting value. At year 0, we're starting at $10,000. So y equals 10,000. And our growth rate is the common ratio that we found, the 1.1. So b is 1.1, and we leave x to the exponent x because that's our time in years, and that's something that can change. So check the equation for t equals 6 years. So if our equation is correct, if we put 6 as x, we should get the value that is in our table here. So y equals 10,000 times 1.1 to the exponent 6. And we get 17,715.61 as our answer. So that gives us the verification that our equation is right. And for D, find the value after 20 years. So for x, we're going to put 20. Y equals 10,000 times 1.1 to the exponent 20. Okay, so in your calculator, make sure you do the exponent first, so 1.1 to the exponent 20, and then we multiply that by 10,000. So when we do that, we get $67,275. So we have looked at the equations, graphs, and table of values for linear, quadratic, and exponential. So the difference between those. An equation for linear is in the form y equals mx plus b. An equation for quadratic is y equals ax squared plus bx plus c. And for exponential, we have y equals ab to the exponent x. Talking about a graph, if it's linear, we have a straight line. It can be a positive line. It can be a negative slope. If we have a quadratic, we have a parabola. So it can be a parabola that faces up, or it can be a parabola that faces down. But it's something that bends around. And if we're talking about exponential, we know that we have exponential growth as an option and exponential decay as an option. Okay, so it still has a curve like the quadratic, it just doesn't bend all the way around. It's always increasing or always decreasing, where a quadratic can be increasing and decreasing. And for our table of values for linear, the first differences are the same. Quadratic, the second differences are the same. And for exponential, we have a common ratio, which means we're dividing. Okay, with our differences, we are subtracting. Okay. So comparing all of those different models in the questions from your textbook. If you have any questions, please let me know.